Hoodie Math brings you example number 2 from 3.6 Mechanical Vibrations. This is differential equations at Williamsfield High School. Holla at your boy. The hoodie is a thing. So, without wasting too much more time, put in your earbuds. Let's initiate this. It's time and place for your educational greatness. If you didn't already know, now you know. We're starting with a free body diagram. There is my spring. Here is my mass. We're going to have a dampening force. FD, just got an email. And my two puppies are arguing over a toy. So if you hear some growling, that's them. What we have here is a similar problem to what we just saw in example 1. We still have a 16-pound object. And what we found originally is that mass is 1/2 at that point. We also knew that K was equal to 18. Now I'm going to show you a little bit of something I showed you in the first video. The change in X times K equals mass times gravity. And in the last video, I just called that L without really talking about it. We did solve for the change in X in the original, but now we're solving for K each time. So K is just equal to mg over the change in X. And I didn't really go over that too much last time. I just called it L. And in the same case, if we do that again, we have the very same thing. We have 1/2 of 32 over the change in X 8/9. And if you remember from the last video, K equals 18. So we have those things. But in this problem, we do have a dampener. The dampener has a force of 12 pounds and the velocity is 2 feet per second. So going back to that first video again, F of D equals C times your velocity. And again, that represents your velocity. So if you know the force is 12 pounds, and you're trying to find C because you know the velocity, then C is just 6. Again, let's lock that in. So this time we do have a C where last time we didn't. But again, no external forces. So when we have F of T, that's going to be equal to 0. Again, mass times gravity cancels out, but it's still there. So the sum of forces again in your differential equations, remember it's modeled by this function, by this scenario, this differential equation on function. Whole lot of hodgepodge going on here. That's an equal sign if you didn't know it. Now you know. So the equation we should have is 1/2 x double prime plus 6x prime plus 18x equals f of t, which is 0 in this case. Again, just like the last problem, we don't want that 1/2 in front. We want to clean it up just a tad bit. So, Marley, that would be enough from you. Girls, you know who I'm talking to. Stop. I'm making a video. Daddy's making a video! Yeah, that's happening right now. They don't care. And then I get emails on emails. I think this video is going to stay. It's like the blooper reel. R squared plus, you know how many videos I've made that I haven't used? Too many. Too many to count. Alright, so we are going to factor said thing, and that would factor into R plus 6, R plus 6, so it's the same. R case number 1, 2, or 3, guys. Yeah, that's case 2, because it's the same. So, upon further analysis, we know that case 2, and you know I'm going to write the original, although if you want to save time, I wouldn't. Just trying to do a quick review here. There's your case number 2. So C1e to the negative 6t plus C2t e to the negative 6t is our function. Alrighty, so we know exactly what we're going to do here. We're going to take the derivative. Derivative. Negative 6c1e negative 6t. That was easy enough. And then this, take the derivative of t first, so that goes to 1 plus c2e the negative 6t. And derivative of that, t stays, negative 6 drops down, negative 6c2 t e negative 6t. Hopefully I got that in there and you can read that. So we have the initial values with the same as originally. Remember, this one was in inches upwards. We know that going down is positive from our initial value. X of 0 equals negative 1/2, and x of 0, x prime of 0 equals 1. So let's plug those bad boys in. Let's finish up the shenanigans. Negative 1/2 equals C1 e to the 0, and that's going to 0 because of that t right there. If you didn't see that, I'm sure you did. And so negative 1/2 equals C1. C1 done. Now let's do C2. So plugging in 1 equals negative 6C1 e to the 0. So we will keep track of that C1, and then obviously that one's going to 0, but this one is not. So C2 e to the 0 minus 0. Plus 0, because why not? All right, so we know C1, negative 1/2. So plugging in negative 1/2 times negative 6 gives us 3. And it's just a little bit of arithmetic from there. C2 equals negative 2. And now we have our final C value. And to model this spring, the differential equation is, let's write it in green, x of t equals negative 1/2 e to the RT minus 2t e to the RT. Holy shenanigans, that's terrible. Kind of forgot the 6 that we had. Again, an email to finish off this video. And buddy boy, that was a negative 6. Don't make the mistakes I'm making. So it's this guy in the bottom. Negative 60. So negative x of t equals negative 1/2 e to the negative 6t minus 2t times e to the negative 6t. That is the differential equation that models this scenario for this spring, the mechanics of this spring. I think that's pretty cool. We have to create a lot of differential equations to model things in life. The more complex it is, the more variables, right? The more variables we add, and that's why we keep adding these t's we've seen in all these differential equations. Have a great day.